afternoon. My name is Anthony and I'm a software engineer at Canva. Canva is a global online visual communications platform on a mission to empower the world to design. I'm in Canva's cloud security team and we have been responsible for the rollout of HashiCorp Vault. We're on a mission to make Vault the source of truth for all static secrets and eliminate long-lived credentials. I'm very excited to be with you here today, all the way from Australia, as Kelly said, to talk about Vault, dynamic secrets, and Kubernetes. At Canva, we're using dynamic secrets as one tool to eliminate long-lived credentials. However, we don't just want to use dynamic secrets for the applications we develop in-house. We also want to use dynamic secrets for the third-party applications that form part of our infrastructure. Migrating these third-party applications that we have no ownership or co-control over presents a huge challenge, however. How does an application which isn't Vault-aware use dynamic secrets? How do we do this in a way that is scalable and reliable? Today, we're going to take a look at how we use the Vault Secrets operator to tackle this challenge and migrate Datadog to use dynamic secrets on Kubernetes with zero code changes. Along the way, we'll also tour the Vault CSI provider and Vault agent injector to understand why VSO really shines. Before I jump into the challenge we faced, however, and how we overcame it, let's take a step back and take a look at Canva's journey so far. Canva's journey with Vault started about 2.5 years ago, and in this time, Vault has had a huge impact on the organization. Every month, Vault vends about 2 million secrets for Canva's build systems. Canva uses BuildKite, and we developed a custom auth plugin that allows BuildKite agents to log into Vault using OIDC and retrieve secrets. BuildKite agents are only given access to secrets for a particular pipeline when they're running a job for that pipeline. When they're not running a job, they have no access to secrets, which is a huge improvement to Canva's security posture. Vault also powers approximately 2 million secret reads for Canva backends every month. Migrating secrets to Vault gave us a good opportunity to streamline the DevOps for secrets management, replacing complex infrastructure as code with an interactive CLI and some in-repo configuration. Finally, PKI. We recently launched an internal PKI powered by Vault. And we have some really exciting use cases on the horizon, like device certificates, which will have a huge impact on developer efficiency and experience. So what's next? Well, over the next 2.5 years, we're thinking about secrets management in 2 dimensions. Firstly, breadth, spreading Vault support across the org and making Vault the source of truth for all static secrets. Here, we've got some more runtimes to support, like AWS Lambda, and we're also looking at things like secret syncing to support runtimes which aren't paved roads and won't be talking to Vault directly. Secondly, what brings us here today? Depth, providing more value for the runtimes that we currently support, so CI and backends, by using Vault to eliminate long-lived credentials. Vault's solution for eliminating long-lived credentials is dynamic secrets. Dynamic secrets are generated when they're required and then revoked as soon as they're no longer needed. As such, they greatly improve our security posture as they have the most minimal attack surface, existing only when required, while only ever being known to the consumer and to Vault. Vault's robust policy system also provides really strong guarantees that these secrets are only available to authorized entities. Looking at the next 2.5 years with Vault, a lot of the value Vault will provide to Canva will be in switching to use dynamic secrets. And as such, this is where we expect our focus to be. With this in mind, about a year ago, we started contemplating our first dynamic secrets use case. We wondered, where should we start? Well, thankfully, this question was actually answered for us with our observability and compute teams coming to us with a problem. At Canva, we run Datadog in Kubernetes to collect cluster and application metrics. Every time a new Kubernetes cluster is provisioned, it needed a Datadog API key, and that was a time-consuming, and manual process that involved humans passing secrets about. Can Vault solve this problem? They asked. Knowing Vault and what it can do, you won't be surprised to find that our very quick and immediate response was yes. However, that was very, very quickly replaced with an uncertainty. How do we actually migrate a third-party application that is not Vault aware to use dynamic secrets? And this is our challenge. So we jumped in, and breaking it down, we identified 3 obvious pieces to this puzzle. We've got Vault, we've got Datadog, and we have Kubernetes. So to start, we focused on getting Vault to generate some dynamic API keys. Vault generates dynamic credentials using secrets engines. Secrets engines are plugins that extend Vault's functionality. They generate dynamic secrets by connecting to other systems and services like Datadog and performing the API actions that are necessary to create a secret. Once the lease associated with a dynamic secret expires, the secrets engine will then perform the API actions that are necessary to revoke that secret. Vault has a number of built-in secrets engines that are available out of the box and can be enabled immediately. Otherwise, for use cases where there is no built-in secrets engine, custom secrets engines can be developed in-house or they can be found open source. Searching HashiCorp's collection of official, partner, and community secrets engines, there were no built-in secrets engines for Datadog. Fortunately, however, we found an open source custom secrets engine developed by HashiCorp solutions engineer Justin DeFrank that we could actually just pick up off the shelf. Vault's pluggability and active open source community was a really huge selling point for us. And in this case, it really saved the day because while it's something that we're doing now, at the time, we weren't really in a position to develop any custom secrets engines. So now that we had our custom secrets engine, we registered it, mounted it, and enabled it at the path/Datadog. We set some root credentials, and then we're off to the races, ready to have a poke around and generate some dynamic secrets. In order to generate an API key, we need to first register a role with the plugin. Roles essentially tell Vault what to create and how. As we're creating bare API keys here, which only just allow the bearer to push metrics to Datadog, the only configuration that we need to give to Vault is a TTL and a max TTL. Alternatively, if we were actually creating an app key, which allows the bearer to perform management actions against the Datadog API, we need to also provide a set of scopes which tell Vault the set of permissions that the app key should have. Once a role has been registered, we poke the Datadog/API key endpoint that's associated with the role, as you can see on the screen, and we have dynamic secrets. We can see that we returned a dynamic API key that's got a lease duration of 1 hour. So now that we have Vault able to generate some dynamic API keys, let's throw Kubernetes into the mix. So at Canva, as I said, we run Datadog in Kubernetes to collect cluster and application metrics. The Datadog agent runs as a daemon set on every single node, and the Datadog cluster agent runs a deployment with a small number of replicas. Today, we're going to be focusing on the Datadog agent daemon set rather than the deployment, as daemon sets are much harder to scale with dynamic secrets, given that they run on every single node. Of the containers running in each Datadog agent pod, we have 1 init container and then 3 containers which require an API key. And all of these containers consume the API key in exactly the same way by this DD API key environment variable. In order to allow the Datadog agent daemon set to request dynamic API keys, we had to register 2 roles with Vault. Firstly, as mentioned, we needed a role with the Datadog secrets engine. Here we chose a TTL and a max TTL of 96 hours so that we'd have a new Datadog API key at least every 4 days. Secondly, a JWT auth role with a policy attached that grants the permissions for the relevant Datadog/API key endpoint. Here, as you'll see, we use a periodic token with a period of 15 minutes. As a periodic token, it will live for as long as it's renewed. Should it fail to be renewed, within the 15 minutes, it will become invalid, and that will cascade to any leases that are associated with the periodic token. They'll also be revoked. You may be wondering why we use JWT auth rather than Kubernetes auth in this case. We actually prefer JWT auth because it doesn't require bidirectional connectivity between Vault and then the target clusters, which makes networking much, much easier. With these roles set up, the Datadog agent could request dynamic API keys from Vault. We just needed to inject them as our DD API key environment variable. Checking Vault's documentation, we knew we had 3 options for injecting secrets on Kubernetes. We've got the Vault CSI provider, we've got the Vault agent injector, and we have the Vault secrets operator. Thinking about the capabilities these technologies needed to solve our problem, as Datadog isn't Vault aware, we immediately knew we had 2 requirements. Firstly, the ability to transparently manage dynamic secret leases on Datadog's behalf. And secondly, the ability to inject the dynamic secret as the DD API key environment variable. However, were there any other requirements? Well, when you take a step back and you compare the lifetime of our Datadog containers and the lifetime of our static Datadog API keys, in the 99.9% of cases, our static Datadog API keys are actually going to outlive our Datadog containers. However, when you compare the lifetime of our Datadog containers against the lifetime of our dynamic API keys, you don't see the same thing. On the happy path, our dynamically generated API keys are going to be valid for the container's entire lifetime. However, in situations where a lease cannot be renewed or has been revoked, the dynamically generated API keys are going to become invalid, and Datadog pods are going to fail to ship metrics to Datadog because they no longer have a valid API key. In order to prevent a metrics outage in these circumstances, we have 2 options. Firstly, we can make some application changes so that the new secret value is picked up by the application without any interruption. Or secondly, we could replace the container entirely so that a new container comes up with the new secrets value. However, as we've mentioned, we have no co-control over Datadog, so application changes are just not an option. We have to go with the replace container approach. So with this understanding, we've got our third and final required capability for the Vault CSI provider, Vault agent injector, or Vault secrets operator. Whatever we choose, we know that it must have the ability to rotate the container in the event that a lease can't be renewed or has been revoked. So now that we've got our requirements, we reviewed each of the options to figure out what would be a good fit. Now, at the time, we were using the Vault CSI provider for static secrets, so it was a natural sort of first step to take a look at this and see whether we could also use it for dynamic secrets. The Vault CSI provider is a Kubernetes native way of working. It's a provider for the Kubernetes secret store CSI driver that attaches a container store interface volume, CSI volume, and mounts secrets into the container's file system. From there, it can sync secrets to a Kubernetes secret object to then inject back into the container as an environment variable. So that's one tick. For dynamic secrets, it can be deployed with the Vault agent as a sidecar to transparently manage dynamic secret leases. So that's 2 ticks. However, it is not capable of actually rotating containers in the event that a lease cannot be renewed or has been revoked, so it can't actually intervene in those circumstances, so there's the potential that we'd end up with a metrics outage, which meant that, unfortunately, the Vault CSI provider was a non-starter for this migration with only 2 of the 3 capabilities that we required. So with that ruled out, we then turned to take a look at the Vault Agent Injector. We didn't have any prior experience with the Vault Agent, however, we understood that it's the tried and true approach for dynamic secrets. The Vault Agent Injector is deployed into Kubernetes as an admission webhook to inject the Vault Agent into pods either as an init container or as a sidecar based upon the presence of certain annotations. Once injected, the Vault Agent sidecar manages dynamic secret leases transparently. So that's one tick. It's capable of injecting environment variables. So that's another tick. And then in the event that a new secret must be leased, when there's a new secret value, the Vault Agent can be configured to send a SIG term to the process that's actually consuming the secret. As that process dies, Kubernetes will very helpfully spin up a new container for us in its place that will, of course, start with the new secret value. So that's 3 ticks. As the Vault Agent Injector looked like it would be a good fit, we moved ahead with a proof of concept. We started by patching the Datadog agent daemon set to include the agent inject and agent pre-populate annotations, as you can see on the screen, that are necessary to have the Vault Agent injected as an init container and as a sidecar. You'll see that we've got the agent init first annotation included to ensure that the Vault Agent is injected as an init container, which initializes before any of the other init containers so that we can make secrets available to them. Vault Agent's templating functionality is also used to inject secrets as files which contain export statements, as you'll see with the agent inject template. So that's the way that the Vault Agent is able to actually inject environment variables. We first inject a file which, as you can see, has the export DD API key statement, and then that is sourced by the container as it starts up, making that secret value available in the application's environment. We then had to patch the command issued to the agent containers. Before making any changes, the command that's issued to the Datadog agent as it's starting up is just agent run. However, as I said, we first need to source the secret files with our export statements. So in order to do that, we modified the command to be a really simple bash script. Wait for the secret file to appear, source it when it does, and then finally run the agent. It was also important to ensure that we didn't use the same secret file path between the init containers and the normal containers, as we learned the hard way. Otherwise, there's actually a race condition where the sidecars will start up with the API key that was used by the init container, which is no longer managed because the Vault Agent init container has already exited. So that's one to keep in mind. And finally, to make this all work and kind of bring the life cycling in, we have to add an annotation which instructs the Vault Agent to send a SIG term to the agent process in the event that a secret value changes. In order to send a SIG term, the Vault Agent has to be instructed to run as the same user, in this case root, and the process namespace needs to be shared so that the Vault Agent has got access to the Datadog agent process. As I've said, when the Datadog agent process receives the SIG term, the container will shut down and Kubernetes will very helpfully spin us up a new container in its place that is going to have the new secret value. So after making these changes, we were ready for a test run, so we applied the changes to our test cluster. And, oh no, it didn't work. The injector refused to inject the Vault Agent container because the sidecar, as you can see in the error message, is not actually allowed to run as root. We did some very quick GitHub archaeology, which showed us that when this functionality was introduced, a restriction was actually added to prevent the Vault Agent running as root. However, it wasn't a technical restriction, so for the purposes of our POC, we called it here, assuming that if we were to go down this path, what we could do is we could just raise a PR to get this restriction dropped. So now that we know a little bit more about the Vault Agent Injector, we took a step back and asked, will it scale? In short, no, for 4 reasons. Firstly, as the Datadog agent daemon set runs on every node with 4 containers requiring an API key, this would result in a huge number of API keys. We run thousands of nodes, which would then result in thousands, if not tens of thousands of API keys. So it would be sailing very quickly past our total API key limit for Datadog, which is in the low thousands. Secondly, this approach is really resource hungry and cost prohibitive with a Vault agent sidecar per node. I was going to try and do some maths for this, but even if we were to assume like a very conservative vCPU request for each Vault agent container, the resources required and therefore cost very, very quickly add up. And I'm quite confident that if we were to go with this approach, we'd have our FinOps team knocking on our door very, very quickly. Thirdly, this approach would result in quite a substantial load increase on Vault, and metrics would be dependent on Vault's availability. Whenever a cluster scaled, Vault would be hit with thousands of really expensive requests that it needs to talk out to Datadog to fulfill. And if connectivity to Vault was lost or Vault was unavailable, what we'd really quickly see is we'd see a metrics outage. Finally, fourth issue, monitoring and availability would be a really huge challenge because we've got thousands of sidecars across thousands of nodes. So whilst we did have what looked like a workable solution, with these concerns, we decided to keep looking, which brought us to the Vault secrets operator. Very fortunately, at the point that we kind of got to here with the Vault agent injector, HashiCorp had just made VSO generally available. So as you can expect, we jumped in and took a look. So the Vault secrets operator is a Kubernetes operator that syncs secrets from Vault to Kubernetes secrets objects. From there, native Kubernetes functionality can be used to inject secrets into pods as environment variables or files. So that's one tick. Vault secrets operator manages the dynamic secret leases here transparently, keeping the value of our destination Kubernetes secret object up to date. So that's 2 ticks. Whenever a secret value changes, the Vault secrets operator can trigger a rollout restart against the entire workload resource, so the daemon set, so that all containers come up using the new secret value. So that's 3 ticks. So we moved ahead to a proof of concept. As a Kubernetes operator, the Vault secrets operator watches a number of custom resource definitions, so CRDs, which tell it what to do. The first of such CRDs is the Vault auth resource, which instructs VSO how to authenticate to Vault. It contains details of the mount path, Vault role, and Kubernetes service account to use when logging into Vault. In this case, as you can see on the screen, we configured it to log in using the JWT auth role we created earlier and the Datadog agent's Kubernetes service account token. When logging into Vault, the Vault secrets operator will be returned a periodic token, which it will renew on Datadog's behalf to actually manage all of these dynamic secrets. Our second CRD is the Vault dynamic secret resource. It instructs the Vault secrets operator to use a particular Vault auth to log into Vault and read a particular dynamic secret path. The Vault dynamic secret resource then instructs VSO to sync the dynamic secret value to a particular Kubernetes secret, and when the Kubernetes secret value changes, perform a rollout restart on the underlying workload resources so that they can pick up the new secret value. As you can see here, we referenced our Vault auth from the previous slide, the API key endpoint associated with the Datadog role that we created earlier, and the Datadog agent daemon set is listed there as a rollout restart target. Finally, after creating our Vault dynamic secret resource, we know exactly where our Datadog API key is going to end up. It's going to end up in the Kubernetes secret object called Datadog-API-key. So we just need to patch our daemon set, as you can see here, to inject the DD API key environment variable from the Kubernetes secret object. Doing so is really nice and clean as we're leveraging native Kubernetes functionality in this case, which allows us to just reference a Kubernetes secret directly. So with these changes, we're ready to do a test run with our test cluster. So we applied that, and it worked. Vault Secrets Operator was managing our dynamic secret, and the daemon set was consuming it from the Kubernetes secret object. We're able to actually see as well in the cluster Kubernetes events which confirm that when the secret value changes, the VSO is actually performing a rollout restart on Datadog. Immediately, one of the things that we really liked about the Vault Secrets operator is just how explainable it is, with these Kubernetes events essentially leaving just a bit of a trail of breadcrumbs, setting out exactly what it is doing. Of course, we can always go to Vault's audit logs to confirm that, but as operators, it's nice and easy to just jump into the cluster and see what's going on. So now that it's working, of course, we took a step back and before considering a wider rollout, considered, will it scale? Well, so firstly, the number of API keys with the VSO scales per cluster rather than per node. So we're only looking at tens of API keys rather than thousands or tens of thousands. So definitely got a leg up on the Vault Agent Injector there. Secondly, resource consumption and the cost profile, therefore, is much more reasonable as VSO runs a deployment in every cluster with 3 replicas for high availability. So FinOps team is happy. That's another tick. Thirdly, observability and monitoring is really easy as we only need to watch the Vault Secrets operator rather than thousands of sidecars. VSO exports Prometheus metrics, which give a really good signal as to the health of the system. If we see an uptick of errors in any particular cluster, we can jump in and figure out what is going on. However, while we had this setup deployed into one of our lower environments, we did actually pick up on one issue. If Vault connectivity was lost for even a really short period of time, metrics would also be lost as the API key became invalid. And to understand why, we've got to do a little bit of maths. So when we decided on a lease TTL, our expectation was that Vault connectivity or availability could be lost for up to 32 hours before metrics would be impacted. So the Vault Secrets operator renews leases at 67% of the lease duration. So under normal operation, there should always be a minimum of 32 hours, so 33% of 96 hours, remaining on a lease if Vault connectivity was suddenly lost. However, what we actually found was that if Vault connectivity was lost for even 15 minutes, the periodic token used by the Vault Secrets operator on Datadog's behalf would become invalid as VSO isn't able to renew it, which would then cascade down to the dynamic leases associated with it. So that means that we're actually only guaranteed 5 minutes, so 33% of 15 minutes of uptime if Vault connectivity was suddenly lost. From a reliability point of view, we were not really comfortable adding such a hard dependency on Vault. So in order to address this, we increased our token period up to 24 hours. This guarantees us at least 8 hours, so 33% of 24 hours, of uptime to resolve an incident in the event that Vault connectivity is lost or Vault is unavailable. When configuring your TTLs for dynamic secret use cases, it's really important to do the maths and understand the relationship between auth tokens and leases as well as the reliability implications. And with that change, we were very happy to say it scales. And after some more testing in our lower environments, we've had this setup running in production for quite a number of months now. So what's the takeaway? Vault Secrets Operator is a huge unlock for dynamic secrets. We've found that the Vault Secrets Operator provides a repeatable, scalable, and reliable approach for migrating third-party applications on Kubernetes to use dynamic secrets. We're really glad that we adopted the Vault Secrets Operator, and it's certainly worth considering for any workloads that you have running in Kubernetes. Thank you very much.